This is an optional step that you might want to do if you're fitting data from fluid inclusions or melt inclusions or anything else where you think you have a secondary phase. That could be a solid phase like a carbonate or a sulfate, or it could be another gaseous phase like SO2 or nitrogen. So what you're going to do is you are going to, first of all, load your Python things. There is actually a version of this notebook that you can use, even if you haven't used DietFit for everything else. So it doesn't actually rely on the peak fitting you did before. It's just going to look and fit the secondary peaks. So there's another example on Read the Docs that I'll link in the YouTube description. But we're going to load in our information we got from step 1, fitting the neon lines. Is just saying where the spectrum are. If you hadn't run the other bits, you would just need to tweak this, and that's in that other example. Okay, so we're getting our diet files. And now what we're going to do is we are going to look at a certain region of space, okay? And we're particularly interested in looking for SO2 here. So what we're going to do is we're going to go through and we're going to set, as normal, our SciPy find peak parameters. And then we're going to run this. And this is basically now running it for every single spectra. What it's doing is it's running through the diode files. All of the file stuff is here. And it's looking for peaks between 1145 and 1155. Any peaks which match these SciPy finding peaks criteria, it will show with a yellow star. And then it is plotting the spectrum over a broader window. So here between 1130 and 1180. You could change this to be whatever you wanted. So you could change this to 1200 so that you get like, you could get the hint of the dyads very clearly. So this is really just for you to help you spot the peaks. You could see that I could shift this. So if I shifted this to 1146, it wouldn't find anything anymore because it's looking for this particular region and there's no peaks in this region which meet these SciPy criteria. So we're using this for SO2 here. You could use this for literally anything you want as long as you know the approximate region of the spectra. It's going to look through every spectra and see if there's any peaks with these parameters within that window. So I'm just going to set this back. And what it's doing is this is a way of plotting it so that each spectra is stacked, so it's normalizing the y-axis. And that means you can look along and you can say, oh, well, K232 fluid inclusion B actually has some SO2 in it. So that's kind of a qualitative assessment of what phases you have. That might be useful. What we can also do is we can basically loop through all of the files where we found something. So what we're doing here is we are looking at, if you look at what this outputs this SO2 peaks thing, okay? So this is, we call it SO2 peak SciPy because there's various ways of doing it. There are other filters you can apply based on sigma, and there's more information for that in the docs. If SciPy isn't working, you're going to want to look at that. But regardless, the output is basically a position, a height, an approximate prominence, and the file name. So you can see it works from the bottom up. So the first file is at the bottom, highest file is at the top. So this peak here is at approximately 1150. That isn't peak fitted with a Gaussian or anything. That's just finding the highest point for now using a spline fit. So what we're going to do is we're going to say we want to get ones where the position isn't an an, because that is where we found something. You might find that you get the odd spike where it finds a peak and you're like looking at it like it's really not a peak. I don't want to do that one. So here we're also applying a prominence filter. So we're only taking peaks that have a prominence of more than 10 units. Anything more than that, like this one down here, we aren't going to use it, okay? So that one is 24, so you can just have a look. Like this, is this really a peak? Kind of looks like the same amount of noise as this. This is why I am discarding it. Okay, and now you can see it has kept 8 spectra, and then it has discarded 1. And these are the file names with SO2 meeting those 2 criteria. So it found a peak and the prominence is more than 10. So if we found any at that point, we would continue running down. This will still work if you didn't find any for the later steps. And now what we're going to do is we're going to think about how we might want to fit this peak. So we can get the relative molar proportions of different gas species by quantifying the area under a peak relative to the area under a different peak. So that's what we're setting up here, okay? So we're setting up a configuration. We're saying we want the background between 1110 and 1130, and the upper background is here. So you can see these are the blue areas on the plot. We're saying that the approximate peak center is 1150. And then we're saying for now that we are going to fit this with a spline, okay? So what it's basically doing is it is fitting a spline and it's taking the area under that spline. And critically, it is taking the peak and it is taking the point at which the intensity is 10% of the total peak intensity, and it's using that for an area. So you can tweak this value. This will depend on your sample. So let's say 0.08. The reason we are having to do this is we find that Gaussian and pseudo-Voigt peaks don't actually fit this very well. You can get a lot of noise with these kind of like little humps on the zone. You don't get very good areas. So this is one way of doing it. As normal, if you want to see the options, you can just do help. And you can see what the options are for this. Oh. Nope, that is not right. Help PF. Okay, so these are basically, you know, these are all the inputs. And one other option is the pseudo-Voigt model, okay? So this is, because this is a configuration file, this is a little bit of a weirder way of looking at it. So you might want to look at the function it's actually being fed into. So we can do that here. We can go help pf.this. And you'll see now these are the different options that you have. So one is the configuration. So we set up the configuration and then we feed it into the peak fit. So the option is you could try with a pseudo-Voigt model instead. So we can try that just so you can see how that would work. So we're going to replace spline with pseudo-Voigt. And you can see that, you know, arguably this is doing an all right job for this. This would be another option. Some of them it doesn't do a great job for. And in this case, it is just taking the area under that curve, which is well defined. So various options there for how you might want to do it. We could also use a Gaussian, which is not spelled like that. So here you see I wrote Gaussian, that wasn't an input. So it's actually telling me that these are the different options. So Gaussian model, Voigt model. So I would have to paste Gaussian model in. And you know, I would say this is a reasonable fit again. It doesn't make that much difference. For SO2, you can actually get away with a lot of the different options. We're just going to use a spline here. There we go. Okay, so we've tweaked that for one file, and now we're going to loop through all of the files where it found SO2. So you can look and you can see it has gone through every single one and it's got the area. So the area is that yellow region. So you might want to look at what this data frame looks like. So this has made this data frame merge SO2. So it has the file name, it has the peak center, and this is now like, you know, the spline fit peak center. If you did a Gaussian or a Voigt, you might get a slightly different answer. It has the peak area of SO2, it has the peak height, and it has the model name that you used to fit it. So you can keep track. So let's just plot, for example, peak area versus peak height, and we can actually see, you know, there's a really good correlation. So this can be helpful if you want to explore things. And the final thing we're going to do is we're going to save this to Excel. You're not going to want to open this really. This is going to get loaded in step 4 and it's going to merge these SO2 peak fits with the diode peak fits. So another common secondary phase in melt inclusions and fluid inclusions is carbonate. So in this case, we are going to be looking for peaks between 1070 and 1100. 1090 is pretty much where you'll typically find something. And you can see actually here, we didn't find any. It found a little peak here. So you can see dolomite is here, MgCO3, the various carbonates will sit in here. So we're not going to define too narrow a range because we actually don't know the composition of our carbonate. And then you would run through as normal. So, you know, it discarded one. It discarded this guy up here because it doesn't have a high enough prominence. This is just noise that Sci-Fi Fine Peaks is filling up. And then it didn't find any. So you can just, you know, run through these. It's not going to do anything. And then jobs are good end. That's step 3B done. You could add as many secondary phases as you wanted. For the actual merging step, at the moment, we support SO2 and carbonate. But if you have other secondary phases, we can easily adapt the code to account for them. So get in contact with us.